Can you all see my screen?
Yes, we can see your screen.
Good. Well, I'm ready.
All right, so our next speaker is Antonio Ley from the Université Laval. He will speak about recent development on the Iwasawa theory of fine Selmer groups.
Thank you for the introduction, and I would like to thank Claude and Florian for organizing this very nice section. I would have liked to participate in Argentina in person, but I guess maybe another time. So I don't assume everyone works in Iwasawa theory in the audience, so I would just give a very quick outline of what we do in Iwasawa theory, at least in some classical setting. So I'll just start with Iwasawa theory for class groups, which is the starting point of the whole theory. So I'll just, for simplicity, assume P is odd and F would be a number field. And I will consider a ZP extension. So here I will have an extension where the Galois group is isomorphic to ZP. And then here I have a sub-extension which is isomorphic to Z modulo P to the N. And then here I'll write this Galois group as gamma, and this Galois group as gamma N. And one object that is very important is the Iwasawa algebra, which is the completed group ring for all this quotient gamma N here, which if you don't know what it is, I'll just tell you it is isomorphic to some power series ring over ZP. And what we are interested in classical Iwasawa theory for class groups is the order, with the p-adic, p power in the class number of Fn as n varies. So the classical result by Iwasawa from the 1970s is that we can actually say what this p order of the class number is, at least asymptotically. So we can say that it is of the form mu times p to the n plus lambda n plus nu for n large enough. And the idea is that how do we do it is to look at the Galois group of M infinity over F infinity, where M infinity is the maximal abelian Pope extension of F infinity, which is a priori can be a large extension, but what you can show is that this group is actually finally generated over lambda, and it is even torsion. So I say that. So here, so lambda is this this ring of power series that I have written down here. So this group is kind of nicely, you can somehow describe the structure of this group. So there's a structure theorem for this kind of module, which tells us that this is pseudo-isomorphic to some quotient by some powers of P, which are, I won't say what pseudo-isomorphism is. It just means that it's, well, I'll say it out loud, but without writing it, it just means that it is homomorphism with finite kernel and co-kernel. So it's almost like an isomorphism. And this integer mu is given by this power of P here. And here, I didn't say what fj's are. So these are polynomials. So remember, we have some power series ring, so we can describe this in terms of just polynomials. We don't need infinite powers. So the lambda here is given by the sum of the degrees of these polynomials. And so you can really describe this formula using something explicit. And then the idea, another key idea is that there's a control theorem which allows you to pass between this Galois group, which is nicely described. So I take the gamma n covariance. So gamma n, remember, is this Galois group here. So I can go from something over the top tower into my finite layer by just taking covariance, and then that would give me essentially the p part of the class group up to some error term. And sorry, this is p infinity. And so using this, we can describe the class number from the structure of this Galois module. So this is the classical setting. So where we look at class numbers for number fields. And after Iwasawa theory started this whole business, there are people who try to understand what happens to elliptic curves. So that's what I will explain now. So for simplicity, I'm gonna assume my curve is defined over Q. And F would just, the ground field I had earlier would just be Q, and the F infinity I wrote down earlier would just be the cyclotomic ZP extension. So, in this case, there's a result by Kato and Wukelich in the early 2000s that tell me that when I look at the rank of my elliptic curve over this big extension, which is an infinite extension, so a priori it's not obvious that the rank of your elliptic curve over this big extension is finite, but that's what they have shown. That they can show that the rank over this big extension is indeed finite, and the technique is kind of complicated. Is using Euler system and some non-vanishing result on the alpha values of E, which I won't go into today. So now another result that I want to explain to you is the result by someone called Jihong Li, who's a student of Hida, who proved recently that okay, so you can say a little bit more about this group. What he showed is that there's a nice explicit description of this group as a lambda module. So you look at this group tensor by QP over ZP, and then you look at the Ponzi eigendual. So this is the Ponzi eigendual. To show that you can describe this module in terms of some cyclotomic polynomials, which is, so it's lambda coefficient by some cyclotomic polynomials. So here, phi ai is given by, well, I'll just write phi n. And so this is for n greater than 0, and phi 0 would just be t. So you can kind of understand what the rank should be in terms of something explicit. And now going back to what Kato and Wukelich did, so they didn't look at this module directly. What people usually do in Iwasawa theory is to look at the Selmer groups, which I suppose most of you have seen. So you have the P infinity Selmer group, which contains this your Moravec group tensor by QP over ZP, and then you have SHA at the end. So we have this short exact sequence. And so now you can ask, well, if I know what the structure of this group looked like, then I can ask, what about the structure of the other two groups? It turns out that is a difficult question. In general, this summer group, the structure of the summer group over the cyclotomic extension has a complicated structure. Is much more complicated than what we have seen for the Moldavie group. It actually depends on the reduction type. So that makes things more complicated. So one nice object that we can look at is, instead of looking at the whole summer group, you look at what we call the fine summer groups. This is in the title of my talk. So it was started, the study of the fine summer group was started by Coates and Sujata in 2005. They look at what I will write as cell 0, which is given by, instead of looking at the whole summer group, you look at the part of the summer groups where you get 0 when you localize it at the primes above P. Okay. So it would be a bit smaller than the original summer group, but the advantage is that this smaller summer group has a nicer Iwasawa theoretic structure. So for example, what we know is that this is also a result by Kato, which tells me that if I look at the fine summer group, which I have denoted by REK here, so I look at the fine summer group over Q cyclotomic, this is always finally generated torsion over lambda. So this is a little bit nicer than the summer group itself, because now for this kind of module, I have a nice structure theorem, as we have seen for class groups earlier. So now, so if we have a substitute for the summer group here, then you can ask, oh, do you have also some similar structure that you can study for the Moldavie group and SHA? So it turns out that this question has been studied by Wolfridge, who was a student of John Coates, who defined what he called the fine Moldavie group. So similar to what we have seen for the fine summer group, you look at the part of the Moldavie group where you get 0 when you localize it at primes above P. Okay. So what's nice about this is that you get a similar short exact sequence as we have seen for the classical summer group and the classical Moldavie group. So this is called the fine Moldavie group, and it sits inside a short exact sequence. So you have the fine Moldavie group, the fine summer group, and then what we call the fine SHA, which is, this is like a Russian letter called Z, if I pronounce it correctly. And so this fine SHA is actually, this is, we call it the fine SHA, which is inside actually the original the usual SHA. And so the conjecture is that the SHA is finite, so that would also imply that the fine SHA is also finite, but it's smaller. So so again, you have a better chance to understand it because the structure would be nicer. So now I want to explain a result that I have proved recently. Is a result about the fine Moldavie group. So here I have the Q cyclotomic. I have to write Kn for my intermediate field. And now I write En for the rank of my Moldavie group over Kn minus the. So this is Z mod Pn. So I want to understand. So I look at the jump in the Moldavie rank as I climb up this tower, and I normalize it by this number. So this is when n is greater than 0. Otherwise, E0 will just be my model vector rank over Q. Okay. So what I can describe is that I look at the model defined model vector group over the cyclotomic extension, and I look at the Pontryagin duo of this group, and I can show, like what we have seen earlier, the results by Lee, who described the model vector group over Q cyclotomic. I can describe the fine model vector group over the cyclotomic, again by some cyclotomic polynomials. So it won't be the same cyclotomic polynomials because I have a smaller group. But one advantage of my results is I can actually describe how many phi I have in terms of my model vector rank. So the number of phi n in the pseudo-isomorphism is equal to this number. I have a little bit more explicit description of this of my structure theorem for the fine model vector group, and the reason is that when I'm looking at this model, this fine model vector group, I can try to understand how it grows in terms of the fine Selmer group. And the fine Selmer group, because it has a nice structure, it satisfies a control theorem that we have seen earlier. So in the beginning, I told you that the class groups in the so the class groups in classical Iwasawa theory satisfy a control theorem of this kind. So what I can, it is a result of by Meng-Fai Lim recently that the fine Selmer groups also satisfy some kind of control theorem. And so using that allows me to understand the growth of my fine model vector rank as I climb up this tower in terms of the usual model vector ranks. And so that gives me a nice description of this module in terms of something explicit. And it turns out that this result seems to be related to a problem posed by Greenberg, who asked the following question: what is the characteristic ideal of the fine Selmer group over Q cyclotomic? And to my surprise, at least when I've proved this result and compare what Greenberg asked, is that he predicts that the characteristic ideal of the fine Selmer group over Q cyclotomic should be given by, precisely phi n to the same expression that I have found. So, so what that tells me is that if Greenberg's problem is true, that means my fine model vector group actually gives me everything that I want to know about my fine Selmer group. And that is equivalent to saying that the fine SHA, I still don't know how to write this, so this is equivalent to saying that the fine SHA is finite. And for me, this is surprising because Greenberg himself has a conjecture to a classical conjecture by Greenberg, which says that the Galois group of M infinity over F infinity that we talked about in the beginning in classical Iwasawa theory is finite when F is totally real and F's infinity is the cyclotomic extension of F. So so somehow, yeah, this equivalence is an analogous statement of a classical conjecture of Greenberg. So I find it very interesting that somehow this fine object seems to reflect better the behavior of classical objects that we've seen in Iwasawa series. So that's what I have found in this setting. So I think I still have 10 minutes. Is that correct?
Yes, it is correct.
Thank you. So okay, so after this result, I want to explain another result that I have studied is when the elliptic curve is supersingular. So I'll assume E has supersingular reduction at P. So E is still an elliptic curve over Q. So for those of you who have seen some Iwasawa theory for supersingular primes, you might have seen this kind of object. So we have a periodic L function, which we call plus and minus periodic L functions. And we have plus and minus Sommer groups, which are well, kind of technical objects, so I won't go into the details. But these objects are, so like I said earlier, Iwasawa theory for elliptic curve somehow depend on the reduction type of E at P. And so at the supersingular case, things are more complicated, and there's this main conjecture relating some periodic L function and some Sommer groups. So again, I won't go into the details. Of these objects, but interesting question studied by Kurihara and Pollack. They want to understand the GCD of these periodic L functions. And they want to know, they conjecture that this should be given by something like this, T to the E0 times the product of Vn. So if you have a good memory, you might recognize this expression that we have seen earlier. So yeah, well, it actually just here. So it's almost the same as what we had earlier, except the exponent at n equal to 0. And these two problems, well, question problem, they are equivalent in a lot of settings. So they're not completely unrelated. There's a reason why they look very similar, because they're measuring similar objects in Iwasawa theory. And so what I can do is, instead of answering this question, which I would have liked to, but what I've done is to define what I call a plus and minus model V group. I'll just quickly write it. I'll just write it like this. I won't again go into too much details. These are just some subgroups of the usual model V group tensored by QP over ZP. And then I have something similar to, I have a short exact sequence like before. I have the plus and minus model V group, plus and minus Sommer group, and I also have some plus and minus SHA that I can define. And these plus and minus SHA, I can show that they are again they are again subgroups of the usual SHA. And my result about these objects is that if I look at the GCD of the characteristic ideal of the plus model V group and the minus model V group, I get exactly the expression Pollack and Kurihara predicted for the GCD for LPE plus and LPE minus. So using this, what I can show is that if this plus or minus SHA over Q cyclotomic are finite, then the question of Kurihara and Pollack has an affirmative answer. So somehow I find it very interesting that all these questions somehow boil down to understanding some kind of SHA to be finite. And I mean, there are lots of conjectures like that about SHA being finite in our subject. So I mean, I don't have any tool to show that these SHAs are really finite, but somehow just by looking at these equivalences that I can show, somehow it suggests to me that there's a good chance well, at least there's a reason to believe why these things should be finite. So, so I think I will just stop here. Thank you for your attention.